In the previous lecture we were discussing about the stress tensor and traction vector and their interconnection. So, we will briefly recapitulate the final expression that we arrived at. So, this is the equation where the traction vector component along the direction 1 for the plane which is having a normal as eta is given in terms of the stress tensor components with along with the direction cosines for eta, that is eta 1, eta 2 and eta 3. So, this you can now write summation of so where j is equal to 1 to 3. Einstein introduced a notation where the summation in a scenario where there are such repeated indices, that summation is discarded just for the convenience in writing. So, this remains invisible, this remains. So, this is written as simply, so the whole understanding is wherever there is a repeated index there is an invisible summation over that. In this case 1 is the index which specifies the direction. So, in general we can write okay, for the direction I, this is known as Cauchy's theorem. So far we have discussed about the linear momentum so far as the conservation equations are concerned. We have of course discussed about angular momentum in the context of Reynolds transport theorem, but we will see that if we give due diligence to the considerations of angular momentum, then how many components are here? I is from 1 to 3, j is from 1 to 3. So, there are total 9 components, but we will find out that out of that 6 will be independent and not all the 9. So, to bring that out, we will briefly have a angular momentum consideration. Let us say that you have a rectangular fluid element like this, with dimensions delta x and delta y. We are considering a 2-dimensional element for simplicity, The reasoning being that angular momentum considers rotation, and rotation in a particular plane may be represented by a simple planar figure. So, let us say that we have our x axis and y axis such that the origin belongs to the centroid of this rectangular element. Now, what will be the forces acting on this? So, let us write here tau 11 times some area. So, here it is tau 11 plus the changed as expressed through Taylor series expansion, that times some area. I am not writing the details because our plan is to calculate the moment of all the forces with respect to this point O, and because these forces are themselves passing through O, they will not have any moment. Similarly, you can have here tau 22 into area, here you have tau 22 plus some change in tau 22 into area. So, the normal stresses are not actually giving rise to any moment with respect to O, but shear stresses will. So, the shear stress so as per our sign convention, because this is a positive outward axis, the shear stress is considered to be in the positive direction, and here because it is a negative outward axis, the shear stress is considered to be in the negative direction. So, what is this one? Tau, the first is the normal direction which is 1, and the second is the direction of force which is 2 into delta y, let us say width is 1. So, into 1, this will be so because we are using index notation, it may not be a bad idea, you know, to write this as instead of delta x1 and instead of delta y delta x2. Just we are trying to use these notations from now onwards. So, to make you conversant with these notations, this is what so in place of delta y we will call it delta x2. All the same, it does not matter, but you know it is consistent with the index. Then this will be then there will be shear forces. So, the name of this is tau 21. This times delta x1. Okay. So, now we will write a simple equation for moment of all forces with respect to O. What is this? This is moment of inertia with respect to O times the angular acceleration. So, when we write moment of forces, see this is tau 1 this is tau 12, this is tau 12 plus a small change which when multiplied by another small length will become much smaller than this. Therefore, effectively both are tau 12 into delta x2 so far as moment calculation is concerned. So, this will give rise to a counterclockwise moment which is tau 1 2 delta x 2 times, this is like a couple, equal and opposite parallel forces, not exactly equal, but the inequality is only in the higher order. So, in the leading order they are equal. So, tau 1 2 into delta x 2 times the length of the momentum, that is delta x 1, this is anti-clockwise, minus this is clockwise, this is equal to moment of inertia, that is basically in this case the moment of inertia with respect to O is 1 by 12 into m into delta x 1 square plus delta x 2 square. So, m is rho into delta x 1 into delta x 2 into 1, this by 12 into this one. Now, you take the limit as delta x 1 delta x 2 tending to 0, which partially we have already taken to ignore the higher order terms. Then if you cancel these ones, because these are tending to 0, these are not equal to 0, then remaining this will be 0. So, right hand side becomes 0. So, you have tau 1 2 is equal to tau 2 1. Remember that this is pretty common, but there are exceptions. When there is an exception, when it could be possible that there is a body couple in the fluid, which normally fluids will not be able to support, but fluids containing rotating particulate matters can support. For example, there are certain types of fluids called as micropolar fluids, where you have rotating particulate elements embedded within the fluid, and then such a fluid as a whole can also support or sustain body couple. So, a big assumption behind this is there is no body couple. If there is a body couple, then this symmetry of the stress tensor gets broken. So, to summarize, from this we can write that if there is no body couple, you will have tau ij is equal to tau ji, just generalizing this. So, there were 9 components of tau ij, but out of that, because of this symmetry, 3 are dependent on each other. So, you will have 6 independent components of the stress tensor. So, with this background, we will now write the Reynolds transport theorem for the conservation of momentum. So, the Cauchy's theorem, which was earlier written as without any body couple, this will become okay. So, now we will let us write the Reynolds transport theorem. For momentum conservation. So, for momentum conservation, if we are interested to write the Reynolds transport theorem, we will write resultant force and this is F surface plus F body, right. In this context actually we started learning the stress tensor and traction vector because we wanted to express the surface forces by certain formal quantities. Next, what we will do is, this is a vector equation, so this has its own components. So we will write the ith component of this, and we will just write this in the left hand side and F in the right hand side. This is what customarily in fluid mechanics we do. In fluid mechanics all the acceleration effects etc. we put in the left hand side and forces we put in the right hand side to describe the equations. This is just a customary way of writing. So we will write the force along I is expressed in terms of the traction vector. Now we will make certain algebraic manipulation. So what is this? So this you can write okay. Just in another way, we can just write it as a dot product of these two, right. So this is an artificial vector that we have created by combining stress tensor components. Sometimes this is also called as a stress vector, but you know this is just a artificial vector created So here what is the index in the vector? Index in the vector is I. So we are just giving it a name tau I with a vector. This is different from the stress tensor. So this we can write, and this is nothing but the unit outward normal vector. Why we are doing all this? We are keeping a strategy in mind, and as a teacher it is very important that we expose this strategy to our students. Otherwise students will try to memorize these derivations, but why we are doing this? See, Reynolds transport theorem gives us an integral equation. We want to derive a differential equation for momentum conservation. So when we want to derive a differential equation for momentum conservation, we will convert all the integrals whatever is there in terms of a volume integral, so that integral of something dV equal to 0, because the volume is arbitrary, that means that something equal to 0, that will bring or that will make an integral form to a differential form. So this poor term had a area integral, so we wanted to forcefully convert it to a volume integral, and that can be possible if we can somehow bring it to a form where divergence theorem can be applied, and that is why we have made this manipulation. This is f dot eta dA, so that will be divergence of f dV. Okay. So here also you see that here already a volume integral term is there, here f dot eta dA is there, we can straight away write it divergence f dV. So only one thing is restricting us, that is this time derivative is inside, this time derivative is inside, sorry outside, we want to bring it inside. Question is when can we do? We have discussed it earlier, we can do only if this V is not a function of time, that means non deformable control volume. So if we now assume non deformable control volume, then let us make all the terms volume integral, this is actually an equation which is mixed vector and index notation based written. So this is a trick sometimes I use in the class. See, we always see our students learn what first, they learn vector first, right, in high school they learn vector first. So vector notations are more convenient to them than the index notations which we slowly introduce to the students. So when we intend to write a index notation based equation, my strategy is I first write whatever I can by simple indices and whatever I can write with simple vectors, and then mix it up and finally bring all to a uniform notation, either vector or index. So that is what I have written here. Now I will just show you how to write the divergence in index notation, because divergence has appeared twice. So divergence of a vector f, so that is so now I am writing x1, x2, x3 because I want to use the index notation. Right. So this as per the index notation you could use any index here because it is a repeated index. Along with this equation, if we want to use, we can use any index other than I, because I is a free index, a free direction that we have already specified, that we cannot use as a dummy index. This is like a dummy index because you are essentially doing a summation. So these will become numbers 1, 2, 3 like that. The index existence will be lost when summation will be done. So, with this notation now, so this is over the control volume. Finally, we will make another assumption. This assumption we have already made, but if it was a deformable control volume, sky will not fall on our head. You can add the effect by another body force, which is because of the deformation. So, when we write this equation in a differential form, we ignore this non-deformable control volume aspect, because whether control volume was deformable or non-deformable, that particular history is completely lost when the volume has shrunk to a point, right. But we have to keep in mind that there could be an additional force and that can be dumped in the body force term. So, then finally, we make another assumption, assume stationary control volume. So, if you have a stationary control volume, then what happens is that the relative velocity becomes same as the absolute velocity. So, Vr becomes V. So, then you are left with this total term in the square box, this plus this minus this equal to 0. So, because the volume choice is arbitrary, that means this term in the box must be equal to 0. So, we have derived the differential equation for momentum conservation . This equation is known as Cauchy or Navier equation. What are the assumptions? See, this stationary and non-deformable control volume, these assumptions can be relaxed by noting that if it was a deformable control moving control volume, there could be an additional term which could be dumped in the body force term. So, with all the additional effects eventually dumpable in the body force term, this has only one important assumption, that is tau ij equal to tau ji, that is there is no body couple. Other than that, there is no serious assumption, because the deformability or acceleration of the control volume can be taken care of through additional body force. Finally, we will make a little bit of simplification of the left hand side, because we want to show a meaning of this equation. You know, this looks like a differential equation with absolutely no perceptible meaning, except there are certain forces in the right hand side. So, we will simplify the left hand side a little bit. So, what we will write is, we will write here we use product rule with ui as one term and rho into uj as another term. So, this we can write, you can take ui as common, plus rho uj, sorry, plus rho as common. Can you recognize what is this? In vector notation, this is divergence of the velocity vector. Just now we have shown the divergence index notation, and this is equal to 0 by continuity equation. So, this will become the left hand side So, the same term, this particular form is called as conservative form. Why it is called as conservative form is because this is directly derived from the conservation principle, and this is called as non-conservative form because this is not directly derived from the conservation equation, but conservation equation in conjunction with continuity equation leads to this simplification. The conservative form is used in those computational fluid dynamics techniques where the conservative forms of differential equations are integrated to discretize the equation, for example finite volume method, whereas non-conservative form is commonly used for analytical solution because it gives rise to a simpler expression as compared to this. But the beauty of the non-conservative form is that it directly gives you the physics of the problem. So, what is here? This you can recognize is the acceleration of flow, right. So, this is acceleration along the ith direction. This is the total derivative, this is essentially dUi dt. So, this is rho. So, if you multiply by volume, then that will be mass. So, mass into acceleration. So, this left hand side therefore is mass into acceleration per unit volume, and right hand side is force per unit volume. One is surface force per unit volume, another is body force per unit volume. So, this is essentially Newton's second law written in Eulerian coordinates, nothing more than that, where this is mass into acceleration per unit volume, this is force per unit volume. With this little bit of note, we stop here and we will continue in the next lecture.